Hello and welcome. We will go ahead and get started. Welcome to our webinar on Foundations and Beyond, exploring considerations for linear calibration curves. I'll be your moderator today. I am Brandon Cocker, Head of U.S. Sales here at Inorganic Ventures. Just a little bit about myself. I'm a degreed chemist with a background ranging from published co-author in the Journal of Forensic Science to head wine chemist, paint coatings chemist, and so on for 9 years prior to being in a science-related sales role for these past 7. Without further ado, here's our presenter and IV's technical support manager, Dr. Leslie Owens. Dr. Owens is an analytical chemist with research specialties, including chromium, speciation, environmental sample design, elemental spectroscopy, and metal contamination in food products. Dr. Owens graduated from Emory and Henry College with a BS in chemistry and a minor in mathematics. Dr. Owens, a Cunningham Fellow, received her PhD in analytical chemistry from Virginia Tech. As we get started, please feel free to ask any questions directly in the Q&A section, and we will address them at the end of the presentation. Dr. Owens, the floor is yours.
In today's presentation, we will briefly talk about the purpose of calibration, then take a closer look at the most common type, direct calibration, or the calibration curve method. We will review the basics of direct calibration and conclude with a discussion of more advanced topics, such as forcing the y-intercept to 0 and curve weighting. In general, calibration is used to relate a response from the instrument to a parameter of interest. Usually this is establishing a relationship between the signal intensity and concentration. For ICP, the signal is a peak intensity at a particular wavelength for OES, or a mass intensity at a given mass to charge ratio, or M to Z ratio, for mass spec. This relationship is established by introducing a solution of known concentration, or what we call a standard, into the instrument and plotting the instrument's response as a function of concentration. This information and relationship is then used to determine the concentration of an unknown sample based on the sample's signal intensity. Today, we will focus on the direct calibration or the calibration curve method. As I mentioned earlier, this is the most commonly used calibration technique. I'm sure each of you uses this type of approach daily. At Inorganic Ventures, we use a calibration curve to check that our multi-element standards have been prepared correctly. For direct calibration, signal is directly proportional to analyte concentration. A curve is generated using a series of standards. For the remainder of this talk, my use of standard will refer to a CRM or a dilution of a CRM or certified reference material. Standard concentrations are selected such that the sample is bracketed by 2 standards. So you'll need to have a ballpark understanding of the unknown concentration for this approach. For example, if a sample is suspected to have a concentration of 20 ppm, then the calibration curve should have a point higher, say 25 or 50 ppm, and a point lower, something like 10 ppm, to bracket the sample. The wide linear range of today's instruments allows users to create calibration curves over several orders of magnitude, which makes bracketing possible for nearly all applications. The calibration curve generated from a direct calibration looks similar to this. A linear regression, or y equals mx plus b, is applied to the data, and error bars can be used to show the variability in signal and consequently concentration. Error bars represent the variability in the measurement. On the y-axis, this is a function of the standard deviation of the signal, and on the x-axis, this error is used in the error budget to estimate the uncertainty in concentration. In general, error is highest at the ends of the calibration curve and smallest in the middle. You can think of the error as a bow tie-like shape, smallest in the middle, and it flares on the ends. This is one of the reasons that check solutions, or QC solutions, are typically analyzed in the middle of the curve. However, you can check elsewhere if you choose, even at the ends of the curve, but your acceptance criteria may need to be larger than what you would use in the middle of the curve. For direct calibration, the term calibration curve is a little misleading. Curve implies that there is some sort of deviation from straight. However, the equation of a line, y equals mx plus b, doesn't allow for curvature. Modern software will allow a nonlinear fit of the calibration data. The goal here is a better fit to the data, and I think the intent is okay, but the practice doesn't resonate with me as a pure analytical chemist. The traditional line model ensures a unique X for every unique Y. So there's a unique concentration for each unique signal intensity. A polynomial fit function with higher powers of X yields more than one value for X for each unique value of Y. Additionally, the error in concentration is more significant in the nonlinear portion of the curve. The increased error associated with the signal propagates to a larger error in concentration. Speaking as a purist, my recommendation is to only use the linear portion of the working curve. If your sample falls outside of the linear region, then simply dilute that sample so that it comes back in range. With advances in semi-quant methods and online dilution capabilities, diluting a sample back onto the curve shouldn't be a problem or cause you that much more effort. It's important to understand the linear range of your instrument as well as your limits of detection and quantification, as these parameters will help inform the calibration range. Linearity of the instrument is determined upon instrument setup. Method linearity, on the other hand, will almost always differ from the linearity displayed during setup. You should be aware of this when validating your method and establishing method-specific linear ranges and limits of detection and quantification. This will help prevent unreasonable expectations for the limits in your method. The limit of detection is defined as the smallest quantity of analyte that is statistically different from the blank. This is calculated as 3 times the signal-to-noise ratio, or 3 times the standard deviation of the blank divided by the slope of the calibration curve. The limit of quantification is defined as the smallest amount that can be measured accurately. Here, we're concerned about more than just seeing the analyte. We want to measure that analyte accurately, so the value is approximately 3 times higher than that of the LOD. The LOQ is calculated as 10 times the standard deviation of the blank divided by the slope of the calibration curve. I like to use the following picture to visualize LOD and LOQ. So let's take a closer look at these Gaussian curves. The blank is on the left and the sample is on the right with concentration on the x-axis. For the blank, there's an equal probability of being above or below the average blank signal. You want your sample curve to be separate from your blank curve, not on top of each other. The area under the tail of the blank on the right side is what I want you to focus on here. If the curves overlap, there is a 50% probability that your sample doesn't contain the analyte of interest. When we move the sample curve to 3 standard deviations to the right, there's only 1% of the blank curve that is above the detection limit, or a 1% chance of a false positive. Remembering that probability curves never touch the x-axis, or are never zero, and separating the means of the curves by 10 standard deviations gives us a very small chance that the detected value is a false positive. Direct calibration is great for labs that have a large number of very similar sample types. If the samples in your lab aren't similar or there is variability in the sample matrices, this may not be the best approach for you. Matrix matching your samples and your standards is very important in order to eliminate sources of error in the calibration. This isn't to say that you can't perform direct calibration if your sample matrices are widely varied. It's just a warning to be aware of your sample types and that you may need to use more than one set of standards based on the sample matrix. With all types of calibration, it's important to be aware of potential interferences and be able to provide corrections should you find an interference. Our interactive periodic table has interference information that can be very useful for this effort. For direct calibration, the calibration standards need to cover the range of sample concentration and bracket the samples, as we saw earlier. Working solutions are commonly made from what we call a stock concentrate. The analyst would use something like IV stock 4, shown here, to prepare lower concentration calibration solutions, like a 10, 100, or 1 ppm solution, for example. Dilutions can be performed two ways, either as serial dilutions or as individual solutions. For serial dilutions, the stock concentrate is used to prepare the first working standard. The formula M1V1 equals M2V2 is used to determine how much of the concentrate is needed to prepare a certain volume of a particular concentration. Then this standard is used to make the next standard, and so on. A second dilution scheme involves preparing individual solutions from the bulk concentrate. Using the same concentrations as the previous example, the analyst would use 50 milliliters, 5 milliliters, and 0.5 milliliters of IV stock 4 to make the 100 ppm, 10 ppm, and 1 ppm solutions, respectively. At Inorganic Ventures, we aliquot gravimetrically and recommend that our customers do the same. What does this mean, and how would you do this in your lab? In a gravimetric preparation, the 50 milliliter volume would be weighed on a balance instead of dispensed from a pipette. You can use the solution density to convert between milliliters and grams. There is a higher degree of error associated with volumetric delivery when compared to gravimetric preparation. Air bubbles and viscosity issues are the main sources of error in pipetting, and gravimetric preparation eliminates these sources of error. In the examples shown, a multi-element CRM, IV stock 4, was used as the stock solution or bulk concentrate. However, some analysts may choose to prepare their own stock solutions from single-element CRMs. As a reference material producer with over 35 years of experience, we caution you against this approach. There are numerous compatibility concerns when blending multi-element standards. Matrix, container material, and inter-element compatibility are important considerations. An unstable working solution will wreak havoc in your analysis. This doesn't mean that it's impossible for an analyst to create their own multi-element standards. We just want you to be aware of the challenges and know what the potential pitfalls are. The QR code shown here will take you to an article on our website that discusses reasons why the DIY approach may not be the best option. Ready-to-use standards bypass the problems associated with making your own working standards. Stability is guaranteed for 5 years for the majority of our CRMs, and all documentation is provided. There's no need to train your staff to prepare working standards, which can be a time and a cost savings for your lab. Ultimately, how you prepare your working solutions is up to the needs and goals of your lab. Each method has its pros and cons, so whatever you choose, Inorganic Ventures is here to help with either designing custom standards or troubleshooting any precipitation issues you may encounter. That concludes the basics of linear calibration section. Now let's explore some more advanced topics. From time to time, we get a question about forcing the calibration curve through 0. Customers ask if it's appropriate or recommended to set the y-intercept to 0. In general, this is an acceptable practice if the calibration blank intensity has been subtracted from the intensities of all the calibration standards. It's also a good practice for very narrow calibration windows. I'm talking about curves covering approximately 1 order of magnitude. However, caution should be taken when evaluating the data. Errors can be significant, especially if B, or the y-intercept, equals 0 when it shouldn't equal 0. Whether or not B equals 0 should be evaluated as part of method development and validation activities. You should not just do this on the fly. You should consider the impacts to the data both ways, with and without, and be able to justify using the approach or not. Here are some guidelines for setting the y-intercept to 0. If the blank intensity values are within one standard deviation of 0, you can assume an intercept of 0. A better consideration is the standard error of the y-intercept, not to be confused with the standard error of the curve. When compared to the y-intercept, b can be set to 0 if the non-zero y-intercept value from the curve is less than or equal to the standard error of the y-intercept. If the y-intercept is greater than the standard error of the y-intercept, then the non-zero intercept should be used and the curve should not be forced through 0. Curve weighting is another practice that should be evaluated as part of method development and/or method validation activities. The idea here is to get a better fit for the curve. Traditionally, the error associated with linear regression is higher at the ends and lower in the middle and naturally resembles a bow tie. The intensities and the associated error vary more in these regions due to detection limit issues on the low end and linearity issues on the high end, but all error is treated with the same weight factor. A weighted curve attempts to minimize the overall error throughout the curve by downplaying the amount of error at the ends, and curve weighting will assign a different weight factor to each of the calibration points. It basically manipulates the shape of the error distribution. For curve weighting, a test of statistical significance called the F-test is used to compare the precision of the calibration data. In the F-test, we have a null hypothesis, and we set this such that the standard deviations from the high and low calibrators are equal. Our critical value comes from an F table, which can be found in the literature, and the comparison value, F calc, is calculated. For this calculation, we use the ratio of the two standard deviations squared, which is also the ratio of the two variances. Once we have the critical and calculated values, we can interpret the results. If the calculated value is less than or equal to the critical value, the null hypothesis is accepted and the test shows that there is no statistical difference between the precision of the upper and lower ends of our calibration curve. This means that weighting the curve would not be appropriate. However, if the calculated value is greater than the critical value, the null hypothesis is rejected and the test shows that there is a statistical difference. Here, curve weighting would be appropriate. So, to recap, if the F-test shows that the error is statistically different throughout the curve, a weighted approach is appropriate. Most statistical packages can weight curves, or equations can be found in the literature if this is an approach you wish to take. Caution should be taken with weighting calibration curves to lower error. You don't want to minimize too much error and make your results too good. It's better to overestimate error than underestimate it. An alternative to calibration curve weighting is to use more calibrators and/or more replicate measurements to reduce error in the curve, as well as overall error in the results. This concludes today's presentation on linear calibration. To summarize, we covered the basics of linear calibration and discussed some advantages and disadvantages of this popular calibration technique. Then we briefly discussed the more advanced topics of y-intercepts and weighting calibration curves, as well as considerations for when to use these techniques. Thank you for your time and attention. Please visit our website to see all of our technical resources.
Thank you, Dr. Owens. We'll continue on. We'll start answering some of the questions. We'll start with the first question. What are your thoughts on quadratic fits? I often use linear or average responses. If I have to use a quadratic, is there anything that type of curve is telling me that could be important?
Right. So, as I said in the presentation, I am linear regression. I acknowledge that there are other techniques available, but I would prefer to see things on a y equals mx plus b and not looking at higher orders of x. And again, it's the one-for-one relationship there that I would prefer to be in. You can always split up your curves if I think the quadratic helps you extend the range of your calibration curve. But, if you've got a large number of samples that are in the low end and, a fair amount of samples in the high end, you can always separate those curves so that you're working in linear regions in both of those areas. So I would just, caution against, making sure that your error doesn't explode too much as you're getting to that upper end of the curve and you're starting to fold over into that flat region. So that's just my word of caution for nonlinear calibrations.
Next question is, what's the difference between standard deviation and standard error, and when should I use?
Right. So both terms are looking at variability of a measurement. So standard deviation is going to look at the variability within a single sample. So one calibrator, for example. So all those replicates that you're looking at for one particular sample. Standard error is going to take that across more than one sample. So your calibration curve, for example, right? So the difference between the two is the standard deviation is the difference between each individual X value and the mean. And then that's divided by, you square those to keep them positive values. And that's divided by n-1. And you take the square root of that. And then the standard error is going to be the standard deviation divided by the square root of n. So again, we're just looking at different pieces, right? Standard deviation looking at one particular sample, standard error is going to look across samples.
Next question is, what does R squared mean in linear regression?
So in really simple terms, R squared is just going to tell you how well your data is fitting to linear regression. We call this goodness of fit sometimes. 1 is a perfect value, and that just basically says your data point is on top of the predicted line. So that's ideal. So typically, this is a measurement of the sum of the squares of your residuals divided by the total sum of your squares. So looking at the distance between the data point and the predicted value in your regression, and then looking at your value, your individual data point and the mean value. So it's just trying to get an idea of how good this fit is. R squared acceptance criteria is typically set during your method validation activities. 1 is what we're trying to go for all the time. That's not always possible. There's error in every measurement. So you're never going to get 1 all the time, but you have to decide what's acceptable in your method. How much error are you going to allow in that calibration curve?
Next question is, what is suggested when it comes to forcing through 0 versus forcing through blank?
Right. So that's the idea of whether you want to take a y-intercept that's non-zero, which is typically what comes out of your calibration curve, versus forcing that value through 0. So I typically say, I would take it where the blank is versus moving it to 0. But if you've got a well-characterized blank and your samples are, very similar to what this blank is, then there's no problem in forcing that through the blank, which you could call that your 0 point.
Next question is, if you get a concentration a little higher than your highest standard, how can you tell if that is a reportable/valid or not? How do you decide?
Yeah, so I would take a look at that in terms of, trying to find if there's a reference material that you could compare to. So if you're getting results consistently on the high end of your calibration curve, take a reference material and run that through your process and see if you're getting back acceptable results for that reference material. And then you could always see if you could expand your calibration curve too. So, I would say comparing that to the reference material and then considering expansion of your calibration curve when you get higher values.
The next question is, if you fit the calibration curve to 0, can you consider 0 a calibration point that brackets your sample?
It depends on how well your instrument is looking at that 0, right? If you've got a high degree of variability in that blank, then you may not want to consider that to be a calibration point in your curve. I typically think that 0 is not a calibration point in your curve, and you want to actually bracket with a sample that you know, and a sample that is far enough away from your limit of detection, and you're in that limit of quantification region where you're really confident that what you're seeing is your actual sample and not a blank.
The next question, I think, expanded on one of the previous ones. It's if the sample concentration is higher than the highest concentration of the calibration curve, the data is valid or the sample should be diluted.
Yeah, I would say dilute that so you're bracketed, but you can always take that approach with the reference material, right? If your reference material is reporting what it should be at the high end of your curve, then go ahead and trust that value. It's all about what you're comfortable in accepting. And, if you're, audited by an accrediting body, what can you technically justify and explain to your auditor that you believe that this result is what you say it is?
The next question is, what is the difference between accuracy and precision?
Right. So accuracy and precision, you can think about that classic example of playing darts, right? You've got the bullseye on the dart. So accuracy would mean that we're hitting the center of the bullseye, right? So we're getting the right answer. So our value that comes out of our measurement is what we say it is. 10 ppm is 10 ppm. Precision, on the other hand, is the grouping of your data. So you can group everything on the right side of the dartboard, so you're highly precise, but you don't have any accuracy. You're not in the center of that dartboard, right? So ideally in your measurements, you're shooting for accuracy. We want to hit 10 ppm if that's what we think it is. But we also want to make sure that all of our measurements are tightly grouped in the same area.
The next question is, what are your thoughts on forcing the calibration through 0 regarding matrix effects?
Yeah, so forcing through 0, you're going to have to make sure that you have a matrix that is the same. Your calibration standards and your samples are matrix matched. So if you don't have matrix matching, you could see some matrix effects, right? There's viscosity issues that you could see from the nebulizer and so forth when you're in a mismatched situation. And I would be highly cautious in forcing that through 0. I would first up, match if you can. The next step is making sure your internal standards are functioning properly. Any sort of matrix mismatch issue, I'm always looking for my internal standards to make sure that that's performing the way we're supposed to, and also understanding what the internal standard correction would be doing in those situations. But yeah, I feel like if you're highly matrix matched throughout your calibration, throughout your samples, then forcing through 0 is a little less risky.
The next question is, what is the reference material?
Right. So reference material could refer to a real world type sample. That's how I'm using it when I'm responding to these questions. So I think of a sample that you would prepare like you would one of your other samples. And so what you're doing is you have a known value. You think of this as your known unknown. So you would take it through your sample preparation, then you would run it as a sample. And what you're looking for is to get back the certified value or the reference value for this particular material. So this is what you could call a true. So this is, say, 10 ppm, for example, in fish tissue or something like that, right? So you would be looking to see how well your method is performing according to this reference material. Reference material says I should be 10 ppm. Did we get it right?
The next question is, how often should you determine / recheck a method's MDL or LOD?
Yeah, so I would say, you know, this is going back to the idea of method validation. And if anything changes in your method, you're going to have to go back and look at all of your parameters and make sure that you're still within the acceptance criteria that you've set for your method. You know, typically you've got SOPs and nothing is really going to change from, you know, day to day in your operating. What is really critical here is that you set or your method validation activities are robust, right? You're creating a very robust method so that the small changes aren't affecting your limits of detection, limits of quantification, and that you don't have to go back and revalidate and reassign these LOD, LOQ values.
And I believe the final question, unless we have some more come in, is for the matrix effect, do you think it is a better idea to digest the calibration solution also?
I think it's a good idea to run a calibrator through your sample preparation process and then kick that back as a sample onto your calibration curve to see if there is any effect. You know, these reference materials would be a great place to do this as well. Yeah, I think it's a good idea to make sure that the actual sample preparation process doesn't do anything to affect the calibrator solution as well.
If we don't have any more questions, please find this recording on our website shortly. You'll be able to find additional webinar recordings there, as well as our interactive periodic table, ICP guide, and many other resources. Feel free to reach out regarding any additional webinars you would like to see in the future. Additionally, though we have sold out all the tickets for the ICP conference here in September, stay tuned for information on additional conferences or an additional conference we will be having regarding the ICP conference in December. Finally, on behalf of everyone here at IV Labs, I'd like to thank all of you for your attendance and continued interest in the science community.